In this video, we're going to take a look at Fibonacci numbers, which together we're going to call the Fibonacci sequence, and then we are going to tie that in with what's called the golden ratio. So Fibonacci numbers are the sequence that we see here on screen, 1, 1, 2, 3, 5, 8, etc. And the idea is we start off with those two numbers, 1 and 1. Every other number after that is just by adding the two preceding numbers. So basically what that means is we start with 1 and 1, and then we say, okay, to find the next number, I just add the two numbers that came before it. So 1 plus 1 would be 2. In order to find the next number, right, 3, we just do the two numbers that came before it, 1 plus 2. So that's how we find that sequence. This is a very well-known sequence. You might have heard about it before. And a couple places that we see this in nature, which means there's really something to this. There's some sort of efficiency in the sequence. But some places we see this are pineapples. So there are actually a couple different ways that we see it on the number of, I don't know what you would call these little guys, but they're little hexagon pieces here on a pineapple. So depending on the angle that you go across that hexagon, you're going to come up with some number in the Fibonacci sequence. There are, typically these are the type of pineapples you just find at the grocery store. You could check these. But yeah, they tend to be numbers, and you have to just kind of follow it around the pineapple in some cases. So like the green one that you see here, right, you'd have to keep wrapping around to see how many numbers it is. So typically, if you go from top to bottom, you'll get something like 8. If you go at a slightly more diagonal, 13. If you go like the green one, you might get as much as 21. We can also see this in pine cones. There's not really a necessary relationship between pineapples and pine cones. But again, sort of spiraling around from, this is a top view of a pine cone. So if you spiral around and count how many little pieces of pine cone you encounter, again, those will be some of the Fibonacci numbers. And in flowers, there's a couple different ways that these show up. So one is just the number of petals. But another, you kind of see this spiraling type of pattern, like overlapping spirals inside this flower here. And it's, if you really zoom in and count these guys up and follow one of those spirals around, you end up getting, well, really two properties, but in particular, one is the number that you pass by is going to be one of those Fibonacci numbers. So anyway, let's show how we find the third, fourth, and fifth Fibonacci numbers in the sequence. We did this just very briefly up at the top. So I'm going to spread these out a little bit. So the first few numbers look like this, right? And then we carry on. So we said, okay, 1 and 1, those are just fixed positions. But to get 2, we just add the previous two numbers. So 1 and 1. To get 3, just add the previous two numbers, 2 and 1. To get 5, we add the previous two numbers, so 3 and 2. And to get 8, we just add 3 and 5. So nothing too crazy there. It's pretty straightforward. And in fact, I will have you calculate, basically come up with a way to do this in Excel so that it calculates this for you. Basically, once you have the first two numbers, it'll calculate as many from there that you want. One additional place where we see those Fibonacci show up, Fibonacci numbers show up, is the golden ratio. So the golden ratio is kind of famous for a variety of reasons, but it is denoted by the Greek letter phi or phi, depending on how you choose to pronounce that. So I generally say phi. So phi is actually equivalent to 1 plus the square root of 5 over 2. So there's an actual proof of how ancient Greek mathematicians found this value using some very basic ideas of just being able to draw a length and use the radius of a circle. So they found this value, but the decimal equivalent is approximately 1.618033. The thinking on this is that this provides a nice visual aspect. So something that we use often is called an aspect ratio. So things like computer screens, TVs have this. And a lot of times you'll see these given as 4 to 3. So the width to the height, or 16 to 9, these kinds of things. So you'll see those aspect ratios, and it's just a ratio, again, the width to the height. And so the idea of the golden ratio is that this works as a very nice sort of visually pleasing ratio, 1.618033, to the height would be 1. So again, we can just approximate that, say 1.61 or 1.62, somewhere in that ballpark. So one really common area you'll see this represented by, so again, this is the idea would be the width here is, well, maybe I should use a different color than what's in the visual. How about that? So the width here, it would be 1.61 or 1.62, and the height would be 1. So this kind of creates a nice golden rectangle using that golden ratio. And this is used in the Parthenon, but you know, there's sort of some uncertainty as to whether that actually was the case, or if it was just sort of coincidence and it just happens to be pretty darn close. But there are enough buildings and paintings and things like that that use this ratio that, I don't know, there's probably something to it. We also have something called the Nautilus Shell. So we find this actually in a lot of seashells, but the way that this is created is we use, right, again, the sequence 1, 1, 2, 3, 5, 8, etc. And we say, okay, well, if I start with a square that has a side length of 1, and then I go to the next square, side length of 1, the next one, side length of 2. So we're just using side lengths of this sequence, but we're kind of building on to the shape here. So, right, these two together had length 2, so I could just add the square on directly. Well, okay, now this side length of 2 and the side length of 1, we can put those together, right, and create something of length 3, and then we can put those together. Now we've got, right, 3 from the big one, and then plus 1, so 5. So we create another one here, and then now we have 5 plus 1 plus 2. So, oh, this is 8, right? So this guy has side length of 8. This guy had side length of 5, this guy had side length of 3. So you can kind of see that this spiral gets built from going in this case, a sort of clockwise sort of rotation here to build this, but you can keep building it out, building it out, building it out, and this spiral is pretty well known as well. Okay, so what we're going to do is we're going to find the first few ratios. So this thing I had mentioned was created by finding the first few ratios of consecutive Fibonacci numbers. So again, I'll remind us those first few: 1, 1, 2, 3, 5, 8, and I'll even do 13, and then okay, from there, whatever. So the idea would be take the second number, put it over the first. So 1 over 1. Okay, that's 1. Take the third number, put it over the second. Right? So the bigger number is going to go on top because we're hoping to get the ratio that looks like phi, which is 1.6 and some change. Okay, so that's just 2. So 1 was a little too small, 2 is a little too big. Let's do the next consecutive pair, so 3 divided by 2. Okay, that's 1.5. So 2 was a little too big, but we went back down. 1.5 is a little too small. Go to the next one, 5 over 3. And at this stage, you might start to say, well, yeah, I'm not really sure what that should look like, but I'll just tell you to 2 decimal places anyway, it's 1.67. That's pretty darn close. We go to the next thing, 8 over 5, which is 1.6, even closer. So we start to see that this happens. Now, what I had mentioned in this one was, hey, do this using Excel. And in fact, in the activity, I'm going to have you do this using basically being able to create this as a draggable formula. But here, I'm just going to do it sort of individually. So, okay. Again, I'm going to start here because we're going to use this number divided by this one. Okay. So I'm just going to say equals, let's say 1 divided by 1. And there's the ratio. Let's say equals now 2 divided by 1. Equals 3 divided by 2. So again, I'm just doing the number next to this. So 5, and I could even click on it, right? Divided by the one before it, 4. Equals 8 divided by 5. All right, so I could keep doing this. I could put them in by hand. I could click on these, but the idea would be I should be able to put something, and again, I'm leaving this as an exercise in the in-class activity. I should be able to put something in that very first cell and just drag it down and have it reference these guys on the left side here. But the whole point of this is just to say, all right, eventually if we keep doing this, we should get closer and closer and closer to the real value. And remember, the real value was 1 plus the square root of 5 divided by 2. You don't need to memorize that. I'm just kind of reminding us this is the real value of phi, and so we're trying to get closer and closer to that. And we start off kind of far away, but we're getting closer and closer as we go farther down in these ratios. And I'm sure if we go out to a few more places, which is what you'll do in the activity, you will see we get really, really close to this. Okay, so that's the general idea of Fibonacci numbers and the golden ratio.